in this section, we're going to be talking about the concept of work. We're going to start off with some problems that you probably did very similar to these in high school, and then work our way up to problems where we need to do integration to get some good solutions. But we're going to start off with a real basic little problem. And here's a picture that illustrates the problem. I've got a 50-pound weight up here, and it started down here on the ground, and we've lifted it 4 feet. And the question is, how much work was done lifting that object 4 feet? Okay, well, hopefully you remember from high school, the equation for work is that work is equal to force times distance. Okay, and in this case, the force is constant. Okay, it takes just as much effort to raise this weight from the ground up to 2 feet as it does to raise it from 2 feet to 4 feet. The force stays the same. Okay, because the force is tied to the weight. Okay, and then the distance here is also a constant. So for this example, the work is equal to 50 pounds times the distance of 4 feet, which gives us 200. And my units for this are foot-pounds. So lifting that 50-pound object 4 feet requires 200 foot-pounds of work. Okay, units for work are in 3 different systems. The first one is the one we just used, foot-pounds, where force is in pounds and distance is in feet. Okay, the international system of units the work is in joules. The force is in newtons. And the distance is in meters. And we call that the international system. Another system that's related to that is a little more useful if we're using smaller quantities is the CGS system. CGS stands for centimeter, gram, second. Okay, and the units here, the unit for work is the erg, the unit of force is the dyne, and the unit of distance is, of course, the centimeter. Okay, so just make a note of those units and make sure that when you're doing a work problem that you are consistent and that all of your quantities are labeled with the same set of units. In our remaining examples for this section, we'll be using some well-known physics laws to work our answers. I'm going to give these to you at this point. It's not necessary for you to memorize these or put them in your booklet. Anytime I ask you to work one of these problems, the appropriate formula will be given to you. Okay, the first law is Hooke's law, which has to do with stretching or compressing a spring. So when you see a problem with a spring, you should use this equation, which is F is equal to some constant K times the distance. And the second law is Newton's law of gravitation. And that looks like this. Force is equal to G times M1 times M2 divided by D squared. Okay, G is the gravitational constant. M1 and M2 are the masses of two objects, and D is the distance between the masses. Okay, very similar to this is Coulomb's law. And this has to do with the charges and the attraction between different particles. And this is force is equal to K, where K is a constant, times Q1, Q2, divided by D squared. Okay, Q1 and Q2 are the charges on the particles, and D again is the distance between the particles. Okay, let's look at a problem that uses Hooke's law on compressing or stretching a spring. So just a reminder, we're going to write that up here. F is equal to KD. And I've got a picture of a spring here. And we can see that the natural length, F at 0, no force, this spring goes from 0 to 1.5. Okay, in the second picture, the spring's being compressed 0.3 of a meter, and the force to compress it 0.3 of a meter is 30. And then if I compress it x meters, the formula is f of x equals 100x. So let's write that down. And now listen to the problem. A force of 30 newtons compresses a spring 0.3 meters from its natural length of 1.5 meters. Find the work done in compressing the spring an additional 0.3 meters. Okay, we can use the initial information that was given to us to find a value for K. Okay, we were told that the force required to go 0.3 of a meter, that force was 30 newtons, and that's some constant K times the distance of the compression, which was 0.3 meters. So if I just divide by 0.3, I see that K is equal to 100. So going back to this equation, we've got f of x equals 100x. That's where that came from. So to find work, we want to assume that the force required to compress a spring over a small increment delta x is nearly constant. So the increment of work is as follows. Delta W is equal to 100x times delta x. Okay, in this problem, the spring was compressed from 0.3 meters to 0.6 meters. So this is our equation. The work is equal to the integral from 0.3 to 0.6. Okay, we don't use 0 because somebody else already did that compression. Now we want to see how much it takes to compress it from that first position to a new one. Okay, put in our equation, our expression for f of x, so 100x dx. Okay, easy integration. This is 50x squared evaluated from 0.3 to 0.6. Which is going to give us 18 minus 4.5, or 13.5 joules. In our next problem, we're going to deal with something that's become fairly commonplace, and that's launching a satellite or other space object into orbit. So we've got a picture here showing that we have a satellite that we want to get to 800 miles above the surface of the Earth. For problems involving the Earth, we're going to assume that the radius of the Earth is 4,000 miles and use that. Okay, in this particular problem, we're told that the weight of the satellite is 15 metric tons when it's on the surface of the Earth. How much work is done propelling the module to a height of 800 miles above Earth? Okay, we're not going to consider air resistance, nor are we going to consider the weight of the propellant. We know that as a rocket takes off and burns up its propellant, it gets lighter and lighter. But to simplify this problem, we're going to ignore that fact for right now. Okay, we are going to think about the fact that as the satellite gets further and further away from the Earth, that the gravitational pull is less, so that the weight actually decreases. So we're going to have f of x is equal to c over x squared. Okay, and we want to find that constant c so we can use it. Okay, and we were told that the initial weight was 15 metric tons, so we use 15. And then our distance was 4,000 miles. So this is the weight on the surface of the Earth. This is the distance from the center of the Earth to the surface. This gives us a value for our constant of 240 million. Okay, our delta W, our increment of work, is now equal to that 240 million divided by x squared dx. Okay, and x represents our distance, and our distance is going to go from 4,000 miles to 4,800 miles. So now we know that x is equal to, not 4,000, is equal to 800. Miles. Okay, now we're ready to integrate. We're going from 4,000 to 4,800. $240 million divided by x squared dx. Okay, let's make a little room here. When we integrate, we get that the work is equal to negative 240 million divided by x, evaluated from 4,000 to 4,800. So I end up with negative 50,000 plus 60,000 . So 10,000 mile tons. Okay, we've mixed our units up a little bit here because normally we don't use metric tons and miles together. But since that's what we were given, we'll use that and get mile tons. Okay, if we use the fact that a mile contains 5,280 feet, and that a metric ton is 2,205 pounds, we can convert this, and W is approximately equal to 1.578 times 10 to the 11th power joules. Okay, again, very important in these work problems that you keep track of the units and express your answer in the units that are requested. Okay, this picture represents our next and our last example for this section, and it is a spherical tank for holding liquid. Let me read the problem to you. A spherical tank of radius 8 feet is half full of oil that weighs 50 pounds per cubic foot. Find the work required to pump all the oil out through a hole in the top of the tank. Okay, now this problem is a little bit different because we're dealing with oil and we're pumping it out part at a time. We're not taking the whole thing and lifting it to do work. So as the level of the oil gets lower, the distance is going to get longer if we're going to pump out of the top of the tank. And of course, as the level gets lower, the size of each layer and its volume and hence its weight is going to decrease as these circles get smaller and smaller. So a little more complicated problem here. So we're going to think about this tank, the oil inside, to be composed of discs. And when you see one disc here, and the height of the disc is delta y. Okay, and the radius is going to be x. Okay, you can see a coordinate system here. The center of the tank is the origin, and so the radius of the particular disc of oil is going to be x. Okay, and because the force is related to the weight, we're going to say delta F is equivalent to the weight, which is 50 pounds per cubic foot times whatever that volume is. So we're going to have 50 times pi x squared delta y. Okay, that would be the volume. Okay, for the equation of the circle there, we're going to have x squared plus y minus 8 squared equals 8 squared. Okay, we can rewrite this, do a little rearranging, and x squared is equal to 16y minus y squared. Okay, the 8 squareds are going to cancel out. So now I can write the force increment Remember we started with this, 1550 times pi x squared delta y. So now we're going to write 50 pi times 16y minus y squared, replacing that x squared, delta y. Okay, for our distance, notice that if I have a disk that is y feet from the top, it's going to have to be moved 16 minus y feet to get up to the top of the tank. So now I can use this expression and the 16 minus y to write this equation, or this expression. The change in work is equal to 50 pi times 256 y minus 32y squared plus y cubed delta y. Okay, this tank is only half full, so the y ranges from 0 up to 8 feet, and now we can write an integral for the work. Work is equal to the integral from 0 to 8 feet 50 pi times 256 y minus 32 y squared plus y cubed dy. Okay, the 50 pi is a constant, so I'm going to take that outside and integrate everything else. Which gives me 128 y squared minus 32 over 3 y cubed plus y to the 4th over 4, evaluated from 0 to 8. Okay, all of these are going to be 0 when y is 0, so I only have to evaluate at 8, and I end up with 50 pi times 11,264 divided by 3, which is 589,782 foot-pounds. If you'd like to check your answer, you might think about, well, what if I had all that oil and I just wanted to lift it up 8 feet all at once? You could calculate that, and you would get an answer of 428,932 foot-pounds. Okay, and does it seem reasonable that this number would be a little smaller because I'm lifting everything 8 feet instead of lifting the top layer 8 feet and the bottom part closer to 16 feet? Okay, so this lets us know that our answer is indeed reasonable. When you work homework problems with this, you will not have a spherical tank, so you'll have to work out the geometry for yourself and substitute that in instead of the geometry we used in this problem. Okay, and that's the end of section 7.5. If you need more assistance, please contact me.